In this lesson we will discuss simple OPAmp circuits. An OPAmp is almost always accompanied by some other components in an analog circuit. Generally, it is connected to at least two resistors. The reason is the very large gain associated with OPAmps. As an example, let us assume an OPAmp with a typical gain of 200,000 is connected to two DC supplies of plus and minus 10 volts. To minimize distortion, the output signal will be a maximum amplitude of 20 volts peak. What input amplitude will provide us with the maximum desired output? The gain is equal to the output voltage divided by the input voltage. Therefore, the input voltage is equal to the output voltage divided by the gain, or 20 volts divided by 200,000, which equals 100 millivolts. We observe here that the maximum output will occur when the peak input is a mere 100 millivolts. If the peak exceeds the 100 millivolt value, the output will be driven to saturation, and consequently, the output signal will be clipped. Another problem that can arise, beside the output being clipped, is distortion, even in small output signals. Limitations of upper frequency response could be encountered. Let's now examine some OPAmp characteristics. Oscillations are the result of the circuit producing an output signal with no input signal. Feedback in OPAmps can change the gain of the circuit. This involves a path from the output signal back to the input. There are two types of feedback which are possible: positive and negative feedback. Let's first discuss positive feedback. In this type of feedback, a portion of the output signal is allowed to return to the input in phase with the original input signal. Thus, the input signal is larger, leading to a larger gain and consequently more distortion, lower frequency response, and the possibility of oscillation. Positive feedback circuits are used to construct oscillators. Next is negative feedback. In this type of feedback, a portion of the feedback is allowed to return, having a 180 degrees phase shift with the original input signal. A subtraction results at the input between the input and the feedback signals. The amplifier will receive a smaller input signal, leading to a smaller output signal. The gain of the amplifier is decreased, and consequently, distortion and possibilities of oscillation are decreased, whereas frequency response is increased. Negative feedback is most commonly used in amplifier circuits. The simplest way of providing a 180 degrees out of phase signal is to provide a resistive path from the output to the input. The voltage divider is used since only a portion is fed back. Let's next discuss unity gain amplifiers or buffer amplifiers. The simplest circuit using negative feedback is shown in this figure. The output of the OPAmp has been connected to the inverting input, forcing the voltage to be the same. The input signal is connected between the non-inverting input and ground. If an output load is used, it is connected between the output terminal and ground. On application of a signal, a positive input will force the output to the same voltage level, and both inputs will be at the same voltage. When the input is negative, the output follows the input voltage, keeping both inputs together. The output variation is identical to the input variation in amplitude, resulting in a gain of unity. Also, the input and output signals will be in phase. The circuit is capable of providing a current gain figure of more than 1 and is similar to a common collector amplifier. Next, we'll discuss the non-inverting amplifier. The non-inverting amplifier is similar to the unity gain circuit, except that a voltage divider feedback path is used with two resistors. The output delivers a fraction of its voltage to the inverting input, with the output amplitude higher than the signal input. The current through the feedback resistor is approximately equal to the current through the input resistor, since the input impedance of the OPAmp is very high. The equations shown give the derivation of how gain is determined. We can see that the gain is equal to the output voltage divided by the input voltage, or 1 plus the feedback resistance divided by the input resistance. It can be seen that the voltage gain of the non-inverting amplifier is set entirely by the values of the feedback resistor R sub F and the input resistor R sub I. The minimum gain value of 1 is obtained when R sub F is shorted. Normally, these resistor values are selected from 1 k ohm to 1 megohm. Any gain can be produced by selection of the resistor values. It should remain less than the open loop gain of the OPAmp. Because the input and output are in phase with each other, this OPAmp is called non-inverting. Let's look at an example using the circuit shown. If the feedback resistor is 220 k ohms and the input resistor is 22 k ohms, what is the gain figure for the circuit? The gain is given as 1 plus 220,000 divided by 22,000, or 11. In this figure, R sub F is equal to 200 k ohms and R sub I is equal to 4.2 k ohms. The open loop voltage gain of the op-amp is 200,000. Determine the gain of the amplifier. Since the connection is for a non-inverting op-amp, the closed loop gain is given by the equation 1 plus the feedback resistance divided by the input resistance, or 1 plus 250 k ohms divided by 4.2 k ohms, which is equal to 48.6. When the desired gain is selected, solving for the feedback resistor gives R sub F is equal to the input resistance times the gain minus 1. And in solving for R sub I, we get R sub I is equal to the feedback resistance R sub F divided by the gain minus 1. Let's now discuss the inverting amplifier. The inverting amplifier also uses two feedback resistors as in the non-inverting amplifier. The main difference is that here the non-inverting input is grounded instead of one end of R sub I. This leads to a different type of response for the op-amp. These relationships are shown and give the derivation of the gain equation for the inverting op-amp. We again see that the gain is equal to the voltage out divided by the voltage in, or minus the feedback resistance divided by the input resistance. The negative sign indicates that the input and output are 180 degrees out of phase. Here also, the voltage gain of this inverting amplifier is determined entirely by R sub F and R sub I. Again, when the desired value of gain has been selected, R sub F can be determined. R sub F is equal to R sub I times minus the gain value. And R sub I is equal to R sub F divided by minus the gain value. As an example, if R sub F is 150 k ohms and R sub I is 12 k ohms, what is the gain figure for the circuit? The gain is equal to minus R sub F divided by R sub I, or minus 150 divided by 12, which equals minus 12.5. If a gain of minus 30 is required with a value of 450 k ohms, what must be the value of R sub I? R sub I is equal to R sub F divided by minus the gain value, or 450 k ohms divided by minus the quantity of minus 30, or 450 divided by plus 30 equals 15 k ohms.